Schaefer Lab and a proud member of the board of Thriving Science. Thank you guys so much for coming out on a Wednesday night. I'm super excited to introduce tonight's speaker, but first I've been told by our grand board chair, Diane, that there is a Thriving Science social next week from 4:30 to 6 in the B1 atrium on Wednesday. There will be free pizza, there will be free snacks, and there will be free beer. 3 really good reasons to come hang out for an afternoon, talk to your fellow grad students and postdocs, make a new summer buddy. It'll be great. So we'll see you guys next Wednesday. Just social the whole time, no talks or anything like that. Okay, so I'm super excited to introduce tonight's speaker because he and I went through the trenches of grad school together. So Brad Zamft got his PhD right here at UC Berkeley, mostly in this building, in the Bustamante lab, and we did most of our PhDs together. So basically we're a lab husband and wife. I'm sure you guys have that in your labs as well. He then graduated, left, went to Harvard to work for George Church's lab, was kicking butt there, and then he decided to go ahead and apply for a AAAS. So stop me if I'm telling you any of this wrong. AAAS fellowship, which he won. Went to DC for 2 years and worked for the Department of Energy. And then he went back to the Church lab for a little while, and then moved on to become a program officer at the Bill and Melinda Gates Foundation up in Seattle. He's also traveled all over the world and gotten into some of the craziest situations. So at the beer social afterwards, ask him about all his stories traveling through like Venezuela. Okay? Yeah. So without further ado, I'm happy to introduce Dr. Brad Zamft.
All right. Everybody can hear me? Yeah? Okay. Thank you very much, Alyssa. It's great to see you. It's great to be back. Although I will admit there's like a lot of pain associated. I associate this building with a lot of pain. But thank you guys for having me. Thank you for this awesome turnout. I don't know why you're all here, but you know, I'll talk to you. It's good. And actually, Alyssa just said my whole talk, so there you go. But that's okay. I'll repeat it in more detail. So yeah, the title of this talk is A Biased Random Walk, and my alternative career as a scientist. So my purpose today is to try to just give you an example of a quote-unquote alternative career in science, where one can stay technical but still have it into the neurons. And so if you can couple error rate with calcium concentration, you could make a recording device inside neurons, and you could actually just genetically encode it, so you don't need to like place it into every neuron. You can do you could just genetically encode it, put it into a single cell, have the cell grow up into a person or a mouse, and then all of its neurons will have these recording devices. Pretty challenging experiment. I didn't get that far before I left academia, but you could think that there's other cool applications that you could think about that are maybe not as challenging as putting it in every neuron and having it at millisecond resolution. You know, could you put bacteria that have these recording devices into wells and then be able to record the chemical environment inside the wells? Or could you record the chemical environment inside a gut, which is applicable to a later discussion, or even intracellularly? So this is Plasmodium falciparum. This is the malaria parasite inside a red blood cell. Could you have the malaria parasite reading the chemical concentration that it's affecting inside the red blood cell? So that was interesting stuff in postdoc. But Alyssa asked me to be interactive, and I'm failing, so here's like my one interactive part, I think, so far. Do you guys think that all of that work that I did, putting my head down, doing basic research, was necessary and or sufficient to go into like a policy sort of role? How many people say necessary? Okay. Well, I would say in the particular role that I have, which is staying technical but not being in the necessary but not sufficient. So for all of you that are putting your head down, doing really great research, really focusing on that, that's great, but there needs to be more. But I didn't even know that when I was a grad student. I somehow got these jobs while I wasn't president of any club or anything like that. I wasn't in student government. But what I did do was I was passionate about external other issues, and so I did what I loved. I participated in extracurricular activities, and I ended up mistakenly having quantifiable outputs or accomplishments that came from those things that I could point to either on CV, but also you have to write a lot of proposal narratives or personal narratives when you're applying for these kind of positions, and interviews and things like that. So now I'll just go into a couple of those quantifiable things that I did in grad school unknowingly that really helped me get to where I am. So I lived in the International House. The International House had all incandescent lighting when I was there. So I walked around and counted all the bulbs, calculated the difference between incandescent wattage and compact fluorescent wattage, and I went to the administration. I said, you'd save $30,000 a year, coal equivalent to, or CO2 equivalent to 91 tons of coal, if you change to CFLs. So they did a couple years after I left. I left the International House and lived in the Berkeley Student Cooperative, where in order to pay my way for room and board, I was their maintenance manager. I was basically their superintendent. And the house was very, very interested in decreasing its environmental footprint. So we literally crawled under the houses and put in insulation. We changed out furnaces. We did duct sealing. I did that with a contractor. And that sort of enabled me to become the sustainability coordinator for the entire Berkeley Student Cooperative, which is 15 houses, I believe. It's the largest student cooperative housing organization in the United States. And there I had like a $100,000 budget. I worked with the Berkeley City Council. All of these things I was just doing out of my passions, but ended up being pretty crucial in interviews when people said, yeah, you're a good scientist, but what drives you? Why do you want a policy or sort of broader impact position? I also advised a cook stove company, a company that makes clean cook stoves for the developing world. That was pro bono, but I really liked the work, and once again, I could leverage that in future endeavors. And then I did a lot of travel, as Alyssa alluded to. So, everybody our generation likes to travel. That's nothing special, but you can travel in a certain way, and you can market yourself in a certain way that becomes, something that you can leverage into a future career. So here's, a picture of me in Mongolia, not of me, but a picture I took in Mongolia and in China. The reason why I put those two in there was because that was when we didn't know it, but we had to do a lab move, and we didn't know when the lab move was going to happen. So I went off to China, and then Alyssa actually at that time had to move the entire lab because I was off gallivanting. This is where I was when Alyssa was moving the lab. And then I got accepted into George Church's lab, and I said, can I start in like a month? And then I immediately bought tickets to go to Africa. So here's self-portrait of Africa, of my time in Africa. But this was actually kind of an important trip, right? I went to these little villages. I saw through all my travels, but this is just an example. You actually get to see the problems that are facing the developing world. You get to see, step out of sort of your life and see actually kind of how they live and what affects them. So beyond, talking about it in interviews and putting it on CVs and whatever, it has also driven me in my current work. I think about it every day, when we're discussing, a meeting in London and everybody's flying business class, I think about this kid, right? And so sometimes I fly economy because this kid has never left the village, right? Or, when I have the Huffington Post open on my computer and I'm reading at the Gates Foundation because I'm sort of burnt out, I think, well, my job, every minute that I spend on diarrhea is working for that kid. And maybe I can read the Huffington Post later. So I think travel is actually kind of important. I had a serendipitous, you could look at it one way or another. When I was at ARPA-E, when I was at the Department of Energy, I booked a trip to the Philippines. I did not know, meteorology is not that good, that a month later when I was actually going to go was the largest storm in civilization. So I ended up, instead of having a lot of fun on the beach, I ended up staying a night in this village as the only foreigner, trying to help these people repair their school, spending a lot of time packing rice on trucks, and just gave, I think, a pretty good grounding on really where impact can lie. Okay. So I used sort of all of those kind of things in my personal statements, in my CV, in my interviews to get, as Alyssa has alluded to, the American Association for the Advancement of Science, Science and Technology Policy Fellowship, which I think is a great thing for anybody that's looking to leave academia but use science still as a tool. Sorry for these are definitely like consultant-made slides, but that's the way it is. So, the idea of the policy fellowships are to foster scientifically informed, evidence-based policy, right? They encourage scientists and engineers from a broad range of disciplines to contribute to policy making and learn about policy making and build science and technology capacity. In addition, you learn a lot, right? You learn about the interactions of the branches of government, the sausage making that is the federal budget process, policy making processes. You can go back to academia afterwards, but it's a pretty nice 1 or 2 year experience in government. You get political awareness, etc. And you also learn these things, how to write a memo. The first memo, I still am not that good in writing memos, but the first memo that I had to write took me a week. But these people, it's 1 page, but you've got to get all of biofuel research into 1 page. It's a pretty hard task. So, but those people get really good at it. People that write a lot of memos get really good at it. So you learn how to write memos, you learn how to do kind of strategic thinking, negotiations, things like that. And it's a really, really broad program. There's a placement process. And so you can get placed. You pick who you like. The offices that are looking for fellows pick who they like, and it's a matching process. But it goes, it runs the gambit from people at the State Department, Homeland Security, to National Science Foundation. It's a bit of generalization, but you can imagine if you're working in international, diplomacy for the State Department, you might be doing less science than someone that works at the NSF. So there's a large range, and you have a large opportunity to explore that spectrum. And actually, I learned a lot in that process, in the matching process, because I'd always been a political junkie. I always sort of was wondering, do I want to be like a senator? Do I want to just leave science completely? I still have the science mindset, but not ever read papers again. And then, or do I still really want to stay technical? And in that matching process, I learned that answer for myself. I wanted to stay technical. So I ended up at the Advanced Research Projects Agency for Energy, ARPA-E. It's in the Department of Energy. It sounds like DARPA because it's modeled after DARPA. DARPA is the Defense Advanced Research Projects Agency, which is credited with inventing the internet and stealth technology and GPS. So many people consider it the most innovative funding source in the federal government, so you could imagine why other agencies have tried to copy its process, including the Department of Energy. So ARPA-E has these sort of 3 mission areas: reducing energy-related emissions, improving energy efficiency, and reducing energy-related imports, while at the time ensuring that the U.S. maintains a lead in the development and deployment of advanced technologies. And they do that with this sort of model, this sort of hubris that, unlike many other funding sources, both public and private, we're not interested in just bringing technologies down traditional learning curves, just working on economies of scale or the next iteration of a technology. We want to make new learning curves, right? These kind of disruptive things like cell phones or GPS that totally change the game in the way that a problem is solved, in this case in the energy sector. But as you can see in this graph here, right, implicit in that is you're going to fail a lot. You're going to try to make new learning curves, and these things are just not going to make it due to markets or whatever. And I actually think that this may be a topic for further discussion over beer, but there's not enough risk-taking in any institution that I've been at. People, they say that they're trying to foster innovation, and they say that they are not afraid to fail, but they are afraid to fail. So I've sort of made one advantage of being at my stage in my career where I don't have a huge reputation. I'm not a world expert. I am known as the person that's not afraid to fail in both Gates Foundation and ARPA-E, and I think that's it's important to have people like that. So here's ARPA-E's process. As a fellow, I got to participate in every step, right? Sitting around brainstorming, looking at the energy consumption sectors in the United States and what consumes the most, what produces the most carbon emissions, etc. So the ideation part, then you hold a workshop where you bring together world experts. You create a pitch, an internal pitch that goes to leadership. It gets approved by leadership. Then you start to write a funding opportunity announcement, right? That's a request for proposal, same thing. That's sort of like writing a peer-reviewed paper. It's really rigorous. Then you do review, and then once you have project selection, you go into active program management. That is going on site visits, flying to a different city every week to meet with the grantees and check on them and to work with them to try to use their science towards your goals, right? They're going to be the experts on their science, but they don't necessarily know the priorities of your particular agency. So that's the job of sort of a program officer. So that anybody leave a cell phone outside? Okay, there's an iPhone out there if anybody wants one. Okay, so what did I do? What did I do in ARPA-E? I did a lot of things, and I don't have time to go through probably any of them, or very few of them. But again, I tried to apply synthetic biology to every problem in energy and just see if it stuck, right? So I helped advise. This was a project that was already going when I arrived, to make a program called Plants Engineered to Replace Oil. That's instead of making sugars in plants and then extracting the sugars and then giving it into yeast, having the yeast make biofuels, having to extract the fuels, could you make the fuels in the plant tissues themselves? So you can see how that's like a total disruptive new learning curve, right? I did help create this program which used robots and drones and bioinformatics, hyperspectral imaging, novel imaging techniques to really understand what's happening in plants, particularly biofuel crops, to accelerate the breeding cycles. Because corn is great, but corn has been bred over millennia, and these new biofuel crops, they have like a 7-fold potential gain in their genetics, but we don't want to wait millennia to do that, so we need to have more advanced breeding programs. I wrote a paper with another fellow on the idea that if you could engineer plants to reflect light that is not useful for it, like parts of the solar spectrum that the plants don't use, what would be the implications of that on the water use that the plant needs, and could we reflect enough light to offset some global warming greenhouse gas emissions? And I came up with this idea to do biological self-healing materials. So, the roads that we drive on, the buildings that we live in, they all need to be repaired. There's cracks that happen. And the question, and that's an energy-intensive process to make new building materials. So how does, could we use biology to do that? And then finally, I'll talk about this a little bit. Can you leach metals with bacteria and sequester carbon and make biofuels at the same time? So all of this sort of came through an analysis of what the key sectors of manufacturing, the energy consumption and key sectors of manufacturing are. So you can see that we use 6% of the energy that we consume in the United States goes into making petroleum and coal. 5% goes into chemicals, 2% is the paper that we use, 2% into the primary metals, and then 1% into these materials like concrete. And the carbon emissions impacts are even greater, right? So making concrete is a very, very carbon-intensive process. And so in this particular case, I was focusing on the primary metals. And the question I was asking, the question I was looking at is these huge processes of mining, right? So on the left here, you have the Bingham Canyon Mine. It's the largest excavation, man-made excavation on Earth. I think it's in Utah. It's a copper mine. And it actually turns out that the mining industry also already uses biological organisms to leach the metal. So on the right here, you need a plane to see it, but these are leach pads where they have biological organisms leaching the metals out. The question is, could you take a lesson from like horizontal fracturing to reduce the environmental impact of that process? So instead of excavating in a massive, visible from space mine, could you take what the oil and gas industry has done and turn this massive mine, the Bingham Canyon mine on the left, into this horizontally drilled well on the right? So that picture on the right is they're getting natural gas from that tiny wellhead. But underneath that, about a mile or more down, and miles out, right? They're sampling miles out. So they go horizontal, and they're getting a very, very large surface area, and they're doing a lot of things. But the impact on the ground is just that little tiny wellhead. So the question is, could we do that? And then I don't want to get too technical here. I don't know how people are doing, but it turns out also that these leaching reactions are downhill. They're thermodynamically downhill. They release energy. And what happens now is you just heat, that just gets converted into heat or into biomass. The question is, could you couple it with fuel production, like we do, sugars to fuel, photons to fuel? And so the calculation, the very simple back of the envelope calculation I did, I coupled it to butanol, which is kind of the canonical second generation biofuel. And you get some interesting, very, very back of the envelope numbers. Like, if you were to leach chalcopyrite, that's CuFeS2, for every kilogram, 100% of the delta G went into butanol. For every kilogram of butanol you made, you get an eighth of a kilogram of copper, a seventh of a kilogram of iron, half of a kilogram of oxygen, you'd need a liter of water, and you would sequester 2 kilograms of carbon dioxide. So these are major upper limits. If you took all of the energy that came from leaching chalcopyrite, and if all of copper production in the world came from that process of leaching chalcopyrite, you would save about 0.1% of primary energy by making the fuel and not having to burn a fuel that comes from a fossil source. And it would have a value proposition of like $7 billion, which is nothing if you think about the entire world economy. Iron is a much bigger market, right? That's what it's used in steel production. So if you took all of if all the iron in the world was made from leaching of chalcopyrite, and you kept all of that energy and turned it into butanol, you would offset 6% of the world's primary energy and have about $500 billion worth of products. So the idea here, again, that I proposed to ARPA-E was, can we sequester carbon from smokestack effluent? Can we leach metals? And can we make biofuels all in the same reaction? And what's great about working in a funding agency is that instead of running to the bench and spending 6 years trying to get a result, you can just pay somebody to do it. So we have results. So, here we go. This is a paper that came out not too long ago. You can see on the left the Fe2 curve that's going down, right? So this organism called Acetothiobacillus ferrooxidans, it oxidizes iron. It's consuming iron too. It's growing, so the OD it measures how many cells, the density of cells. It's growing, and it's making isobutyric acid, which is a precursor to butanol. And it's actually as efficient of a process. There's a little bit of apples and oranges comparison here on the upper right, but I won't go into those details. It's almost as efficient, 0.15%, as photons to ethanol going through corn. So they've already got there. They're pretty close just on an efficiency basis. But efficiency is not actually what industrialists care about. The mining guys don't care about efficiency. They care about titer, because they have to extract the stuff from the liquid. So that's where this story is not so good, right? They're making 260 nanograms per liter per day of isobutyric acid. Corn ethanol is on grams per liter per hour, so we are many orders of magnitude off. But this is just one group. This is the second paper that's been published on it. So I'm excited about that work. Let's shift into Gates Foundation. How much time do I have?
Another 15, 20 minutes.
15, 20. I will be early, I believe.
Cool. More questions.
More time for questions. So I'll give a little bit of an overview of this mysterious black box that is the Bill and Melinda Gates Foundation, and then I'll talk a little bit about the stuff that I did. I got this position as a follow-on to my fellowship with the AAAS. So it's another example of how you really, there's a few catalytic things that happen in your life that open up other doors. And it was a biased random walk, right? I had no idea that I was going to work for the Gates Foundation when I started at ARPA-E. Gates Foundation is $4 billion a year foundation, more or less. Here are the offices. But the majority office that STAR is in Seattle. That's where most of the scientists are. That's where about 1,300 people do their job. It's split up into a number of divisions. I work in the global health program, so in the following slides, anything that's in red is something that I have my fingers in. So I'm in global health, which is about a quarter of the budget. Global development is about half. They also have US programs and global policy and advocacy, which I will talk in the next slides. So global health is comprised of enteric and diarrheal diseases, HIV, malaria, neglected infectious diseases, pneumonia, and tuberculosis. And they're charged with sort of solving components of those of the burden of disease of those particular diseases. It's a matrixed organization, which I think is important for people who are interested in going into big organizations to understand what that means. It's complicated. It's much different than academia. But if you think about a matrix, the columns of this matrix are these teams in blue, which are, they have a specific task. They focus on a specific disease, like enteric and diarrheal diseases. These teams that are in orange are cut across, so they're on the horizontal axis. And what they do is they help those other teams. They function as a service for those teams. So I'm in the Discovery and Translational Sciences team. My job is to get the early stage stuff, the sort of bench or slightly past, peer review. I read the literature, I talk to people, and I say, this could have implications in enteric disease research. So then I coordinate with the enteric disease team and fund it in order to get it up to the stage where they would be interested in it. So that's sort of how the foundation works, and it's complicated, but it's actually, I think, quite effective. The Global Development Program has agriculture, which is the largest team in the foundation, emergency response, family planning, financial services for the poor, libraries, maternal, neonatal, and child health, nutrition, polio, and water, sanitation, and hygiene. Maternal, neonatal, and child health should be in red. I do have fingers in there. But you'll notice that there's some health, like polio, you would think should be in the global health division, but it's complicated. So it's just, don't think necessarily that if it's a disease, it's in global health, and if it's a sort of a development issue, it's in global development. The United States program is about education, college ready, post-secondary, and then specific Washington state programs. And then global policy and advocacy, that's when you see Bill Gates shaking hands with Angela Merkel. That's that team that set that up. And I have a program with China, so I sort of interact with them in that case. So Gates Foundation has a very similar process. I think all funding agencies sort of have a similar process in how they make grants. In this case, it's staged. There's 4 particular approvals that you need to get. So you do concept development, you sit around, you brainstorm with experts, with leadership in the foundation who are experts, talk about who would be the right people to do it. You then engage those people, but on sort of an unofficial basis. You talk to the experts, you develop the idea, and once you get this level 2 approval, then you can actually formally engage the applicant and develop the proposal with them. So again, the applicant usually is an expert, a technical expert. They know way more than you about the particular topic that they study, but they don't know the priorities of the foundation. They don't necessarily have a big picture view of the global health priorities, and so they depend on you for that, and you work together. And once you make the funding, once you make the grant, then again, there's active grant management. So you fly out to them, you talk to them monthly, and make sure that they're on track. Here's what I do in the foundation. So I sit in the Discovery and Translational Sciences team, as I mentioned before, in global health. I co-report to the Grand Challenges team and the drugs domain. The Grand Challenges team runs large requests for proposals, large and small. So I co-led a very large one looking for new interventions in global health. This is exactly what it says it is, looking for new drugs, diagnostics, and therapeutics in our priority areas. And now I'm running a similar call, much smaller, with the National Natural Science Foundation of China. I developed this Grand Challenge Explorations request for proposals on bacteriophage-mediated microbiome engineering, which I'll talk about in a second. And then for the drugs domain, I basically use synthetic biology to try to increase the types of chemicals that are present in drug screens, because we really only have tested about 1% of the diversity of products that are even out there in nature. And then I guess because I have a physics background and I have a diverse background, I also have a diverse portfolio. So I have this really cool grant on using detecting volatile organic compounds to see if a person is carrying malaria but not showing symptoms. You can imagine that those people act as a reservoir. We're developing a capsule, a pill that a child can swallow that'll go down their gastrointestinal tract, take pictures, three-dimensional pictures of their gut, and take biopsies. And then I have this really, really fun thing where I get to just go to the Raygon Institute, which is a collaboration between MIT, Harvard, and Mass General. And I just get to listen to professors' favorite projects and then decide, me in consultation with other people, decide how we would want to apply those technologies to our programs. So that's a fun day. So this is sort of long and involved and technical, so maybe I'll blast through it. But I'm going to talk a little bit about my work on this using bacteriophage to engineer microbiota. And like I said, because I'm on the discovery and translational sciences team, I am a service to, in this case, the enteric and diarrheal diseases team. Right? My job is to try to develop new technologies for them to use. And their goal is to eliminate mortality, eliminate under 5 deaths due to malaria in the lower and middle income countries, but also to lower the burden of disease. So not just deaths, but the sickness that's associated with it. And we have been, civilization should just give itself a pat on the back because we have been phenomenal in lowering infant mortality due to diarrhea. So in 2000, 1.2 million children a year died from diarrhea, children under 5. Now it's 600,000. So we've done a huge decline in deaths. But what we haven't figured out is stunting. So children that are low height for age. And that has some sort of nutritional basis, but nutrition doesn't explain the whole thing. So 40% of the children in Tanzania are below the average height for the world. And this is true in many areas, and it's correlated with fitness impairment, which you could imagine, cognitive impairment, so these children are starting, with a strike or two against them. And in the most irony of ironies, we try to give these children vaccines, but because they have this stunting, or because of some process that is involved with their nutrition, those vaccines fail. The very populations that need the vaccines don't respond to them. So we're behind. So here, again, the line is we have a 60% decrease in deaths due to diarrhea, but maybe a 20% decrease in stunting, in the morbidity associated outcomes of diarrhea or of enteropathogen burden. We'll go very quickly through this slide. It's one of thousands of slides that the nutrition community, publishes. But the point is that we've given people food, we've educated people about how to eat, we've given people food that is high in caloric intake, given people food that's high in micronutrient intake, and it hasn't really made the gains that we've hoped. So microbiome to the rescue. So, this is some really fascinating work funded by the Gates Foundation of Jeff Gordon, not the car racer, at University of Washington. So complicated stuff, but if you take a notobiotic mouse, this is a mouse that was born sterile. It had no bacteria in its gut, but you give it a healthy Malawian child's gut microbiome. 20 or 30 of the most important bacterial species that it needs. If you give it that, and then you feed it a Malawian diet, and you feed it milk oligosaccharides, so that's the blue line, you see it grows fine. If you get rid of the milk oligosaccharides, it doesn't do well. If you get rid of the milk oligosaccharides and you give it stuff that's in formula, you can see the red curve. And if you give it nothing, just the Malawian diet, that's the gray curve. So that says obviously that nutrition is important. But then if you get rid of if you use mice that you don't put any microbiome in it, nothing helps, nothing works. So the microbiome is essential to growth. The amount of bacteria the type of bacteria that are in your gut are essential for healthy growth. And this experiment was recapitulated in pigs, which have a better, they're not a perfect animal model for human gut dysbiosis, but they're better. So this has led to the theory of environmental enteric dysfunction, complicated, but the point is that you ingest microbes, you have a dysfunctional microbiota that alters your gut structure and function. It blunts your villi, it impairs the tight junctions between the cells of the gut epithelium, which allows bacteria to get inside your gut, which then causes this inflammatory response, which goes back and damages the gut further, but then also has this growth hormone resistance, impaired bone growth remodeling, increased nutrient requirement consequences, and the villus atrophy is associated with nutrient malabsorption. So that's where the state of the art is on that. But what I felt was important was that when we were doing these notobiotic experiments, which is sort of a synthetic experiment, you take the top 5 or 10 or 15 important bacteria and you make this really synthetic kind of fake microbiome in a mouse. But what about doing the other experiment, right? Can we take a full microbiome, or can we do a fecal transplant from a Malawian kid, and can we delete specific strains, right, one at a time, and see how those are important? So that's how we sort of came up with the Grand Challenge Explorations request for proposals entitled Addressing Newborn and Infant Gut Health Through Bacteriophage-Mediated Microbiome Engineering. And it came out in, I think, May, and then the scientists, they don't say anything about the Gates Foundation in this, but the scientists ran a cover story on the coming of bacteriophage as a new therapeutic for diarrhea. So bacteriophage are viruses, but they only attack bacteria, and they can be very, very specific to a particular strain. And so it's just like about a $5 million request for proposals now, where we have people trying to develop ways of taking out a single pathogen in a gut microbiome. So those are my slides. How did I do on time?
You have 15 minutes left.
We have 15 minutes left. I know that was a whirlwind. The point was to introduce all of those things and then have like a robust discussion on whatever of those topics you're interested in.
So with that, we'll start taking questions.
You want to choose or me?
What?
You want to choose or me? You want to call him?
Yeah, I'll be the bad guy.
Okay.
Questions?
What were the differences you experienced in being like in a public agency like DARPA and a private agency like the Bill and Melinda Foundation?
Okay. Did people up there? Okay. So good question. What are the differences between being in a public agency and a private agency, right? ARPA-E versus the Gates Foundation. It's a good question. I would say that I can only give one answer. There's 175 AAAS fellows per year that will give you a different answer. I was really lucky, in my opinion. ARPA-E, again, was set up on the DARPA model. DARPA model gives a lot of independence to the program directors. They have this thing called direct hiring authority, so you don't have to go through the Office of Personnel Management and all of the bureaucracy there. So it's actually quite a flat organization, quite an agile organization. People can get fired, people can get hired. You can switch directions. Budgets are very flexible. Actually, Gates Foundation, private foundation, it's much bigger. It's tenfold bigger than ARPA-E. So it's actually less agile, even though it's not constrained by a lot of the regulatory, the regulations that federal agencies undergo. So I have a really skewed, but it's an interesting question. I think I can better answer just about scale. So at least in my experience, if you're in a 100-person kind of organization, and that can be within the government, but if it's sheltered, it's its own thing, right? You can really have big impact. You can do crazy things. People are you're friends with your coworkers. If you're at a 1,500-person organization, there has to be process. And so bureaucracy or process sometimes limits your agility. Now, that being said, what's really interesting about the Gates Foundation is that it's an oligarchy. Bill and Melinda Gates decide the priorities. If you manage to convince Bill Gates that dengue is important, then now all of a sudden dengue is important for the entire foundation. So that's interesting. Whereas federal government, you're at the whims of Congress, you're at the whims of some sort of process, large, huge, slow-moving process. Although, again, ARPA-E was set up differently to be somewhat independent. But nonetheless, the priorities of the administration inform what you do. Did I answer it enough?
What percentage of your projects end in a dead end where you have to move on, and how do you deal with that?
Depends on what you mean. I try to make myself a source of fresh ideas. So if that means me studying something for a day and then going to my boss or my boss's boss or somebody else at a higher level than me and saying, hey, I think you should do this, and them saying no, if that's the death of a project, a one-day project, then I am 90% failure. But if you're talking about going through to getting the project funded, identifying an investigator, getting money out the door, I think the VC metric, most VCs will say that, 90% failure, right? And that doesn't mean that you didn't learn something. It doesn't mean it wasn't a contribution. It just means that often the most easy metric is follow-on funding, for better or for worse. So either the project that you liked and that you got funded, VCs took it, or they started a company, or they got bought by a company, or somebody within the foundation, for example, said, wow, that $2 million project, let's put $40 million behind it and really, make a vaccine. That's sort of the easiest way to measure success, and in that case, I would say it's 10% success. But it's actually an incredibly hard question. Measuring success is an incredibly hard question, often discussed. We had a 3-day meeting. We have a 3-day meeting every year on that question. Measuring success in innovation.
How do you emotionally handle your failures?
Yeah, that's why I think it's important to not to consider yourself or be considered an expert. You should not have ego in the ideas that you're bringing forward, right? And you shouldn't be worried about being seen as an idiot. Right? If you approach the problem humbly and with the proper motivation, my true, honest to goodness motivation working at the Gates Foundation is to save people's lives. So when I go up to somebody and say, what do you think about this idea? And they shoot it down, and it's for a good reason, and it's because it's going to be a waste of money, it's not the right priority, we have bigger fish to fry. I'm okay with that. I don't have emotional distress. There are times when the decision is not rational, in my opinion, but that's a lesson that you learn of hierarchy. At some point, those people are paid to make bigger decisions than you, and you have to take them. You can fight a little bit, but then eventually you have to take their decision. The biggest crush that I've had is when there's ego on the grantee side, and they spearhead them. They kill themselves, right? So they're more interested in fame than they are saving someone's life, and those projects end in failure, and that bugs the heck out of me. Yeah.
Both with the same time.
I was wondering if you could speak a little bit about the process of ideation itself and how do you come up with these ideas, and what are some snippets of advice you have for us on honing that kind of skill?
I don't know. I put it out to you. Is imagination innate, or is it learned, or is it both? I think I like to dream. I think I have a good imagination, but I also have technical training. That's where I come from. So I try to dream big. I think the difference, especially at ARPA-E, we got this a lot. We got a lot of people there was a lot of perpetual motion machines. A lot of people that were dreamers in their basement came up with a way to violate the second law of thermodynamics. And they're great ideas, and they're really they're innovative, but they're not based in the principles of science, in the fundamental principles of science. So that's the difference, I think, between what we can do and what the dreamers can do. So what I do, I read papers, I read the scientific literature, I try to see how those things can be applied to problems that those people are probably not thinking about. I do calculations, back of the envelope stuff, make sure that the second law of thermodynamics is never violated. And then once you do that, then you start talking around. Also, what's really nice, like again with DARPA-E, there was 6 other fellows, my age, younger than me, and we just hung out a lot and we bounced ideas off of each other. And those sort of sessions, those undirected hours of just thinking about things, often comes up with an idea that you can then put into that process of doing a little deeper of a dive on.
So you said technical training and background is necessary but not sufficient. Is a postdoc necessary?
Is a postdoc? I realize that I have not been repeating the questions. I apologize. Call me out if I forget to do that again. So the question is, he said, I said that technical training is necessary but not sufficient. Is a postdoc necessary or sufficient? Or necessary but not sufficient? So first of all, let me clarify that the path that I've taken, I have found that my PhD was necessary but not sufficient. That's not true writ large for policy, but if you want to be respected as the technical expert while still working on these things, I think that you need to have the PhD plus other evidence of your passions and your interests. I don't think the postdoc is necessary. No. But you have to have, it gives you an opportunity to maybe develop your portfolio further. That's it.
Did you always have aspirations to leave academia, or was there kind of a switch at some point? And so the reason you took that postdoc, it seems like it was a natural progression from your PhD, which suggests more of an academic endeavor, I guess.
Yeah. So the question was, did I always plan on leaving academia, or was it how did the switch go? I never planned on leaving academia. It was always my dream to be a professor, which is unlike all of my peers in that fellowship, and maybe the reason again why I went into a very highly technical fellowship. But I was torn throughout grad school and postdoc because I noticed that I was just really interested in politics, really interested in a lot of things, didn't want to focus. I still have a problem focusing on one problem, so that wouldn't do well for me if I became an academic. But it took me a long time to let go of the idea. I mean, being a professor is an awesome job, right? You're kind of a king of your domain. You get to play around. You get to do whatever you want, provided you get the funding for it. And that takes 40 years to get the right amount. You have to have an awesome reputation to get funding for whatever you want. So it's actually really hard to get there, but if you get there, it's a dream. But I wasn't willing to put in. I came to the conclusion that you shouldn't live life as a means to an end, right? You shouldn't be constantly working toward. You should live life during life. So that's why I started. It was a torturous process of saying, yeah, I want to be a professor. I want that lifestyle. But I don't want to take 20 years of pain to get there. And so I'm going to try to find other ways to have a similar, I might not ever get my dream job, but I'll get close. And I kind of am close now. So that's maybe a good sign.
Speaking of dream job, is there a way, you spoke about hierarchy earlier, do you feel like there's a potential to move up, or do you feel like it's like a bureaucratic organization where you said it's an oligarchy, so there is a little bit maybe of influence in terms of who Bill Gates is choosing to be higher up, and
Yeah. So the question was, do I see the ability to move up? Do I see the ability to be promoted? And this is an ongoing discussion at the Gates Foundation. This is a identified problem. But unfortunately, I think the answer in the Gates Foundation is no. So the way the Gates Foundation works is they hire people like me, who are sort of mid-career to be program officers. The next level up from me is a senior program officer, and those people did 30 years in pharma or are professors. They've had external careers. And then the next level up from that is deputy director. Those people were deans of departments, things like that. So a lot of these people are in their retirement, right? They're doing this as a second career. And that's a philosophy, and that foundation hasn't always been that way, but they want to have internal expertise. They have amassed a world-class scientific establishment in-house, right? Now, is that the right thing to do? I talked again about you don't necessarily want to have world experts running your innovation programs because their reputation is on the line and they are maybe more risk averse. But that's the way it works. So if I do want to move, I do want to continue on an upward career trajectory. So I would look elsewhere. It means you can come back, right? And so that's true also in the whole random walk. I'm not sure about academia. I have gotten solicited to apply for faculty positions this year and last year. People say once you leave academia, you can't go back. I am not so sure about that. But I think you can go into industry and then go into nonprofit. You can make your name in industry and then become a big player in the Gates Foundation. There's no rules that say we're not in the generation anymore where you work at Ford for like 40 years and you become a VP. I don't see that way anymore.
Did you ever consider, after ARPA-E, moving into a similar position except in industry? So venture capital comes to mind as kind of like a similar job, or working for an incubator or accelerator or something like that?
Yeah, so question again was, did I ever consider after ARPA-E going into sort of going in the private sector for working in innovation in the private sector, right? So VCs, incubators. I totally explored that. I'm open to that. I think VCs are more risk averse than where I am because they actually look for a return. And so they're constrained by capital, by markets, which I agree with. I think markets are good, but they have a more narrow focus. Incubators would be wonderful. All of those things are on the table for me, but I got the position I have now, so I'm happy with it.
So we're actually at 7 o'clock, and I'm sure lots of people would like their beer. So
One more.
One more?
One more.
One more. Who's raising it really high?
Her and then way back, yeah.
Oh, in the back.
So my question is, what skills do you think somebody needs to be successful in kind of each of these different, in academia or in your RPD experience or in the Gates Foundation, and what kind of skills do you need to transition between them?
Wow, I shouldn't have asked for one more. Okay, what skills do you need in each sort of these sectors, right? So academia, ARPA-E, Gates. Okay, so academia, I think people are really selected for their intelligence and their ability to do science. And what I think is really strange is that you become a professor, there's no training, and you're expected to manage people, manage budgets, right? All you've done is you've been a phenomenal researcher, and now you have to do these other things. So that's why I think there's a lot of bad, there's some amazing PIs, but there's also a lot of bad management that goes on there. Whereas that would never happen in the private sector, right? When you're put in a management position where you're overseeing other people, you're getting training, you're getting advising. There's onboarding to learn how to do that. Okay, so academia is really, I'm attracted to it. I respect it because it is a meritocracy, mostly at least. ARPA-E and things like that, you do have to have more skills on making partnerships, on working with other people. You're dependent on other people. The only person that's allowed to sign a grant is the grants manager, right? This guy or girl has worked for 40 years in the government. They leave at 4:59, they get in at 9:01, right? They are not in the academic, hey, let's make a difference mindset. But they are more powerful than like anybody else in the entire agency. So you've got to be good. You've got to be able to work with a broad group of people. And making partnerships, right? When we were doing all this ag stuff, plants engineered to replace oil and these robotic phenotyping. The USDA, U.S. Department of Agriculture, was concerned, right? I mean, we were stepping on their toes. So what did? We we reached out to them, we went to them, we talked to them, we got their advice, we made them a key part of it. So, you know, in academia, you can kind of put your head down, you can just work on your experiment, and if your experiment works, you don't really need to care about, I mean, in fact, you're racing against competitors. That doesn't really work in those other types of positions. You need to bring people on board, or you'll die. All right, beer.
So let's think about it one more time.